Hey class, Mr. Moydin here with a video on how to find the area between two curves, a calculus concept. Notice that I have not given any graphs here, so I'm actually going to look at how you can graph these things when you're not given a picture, because that's a good skill to recall. So one of my functions of my boundary is y equals x squared, so that's just going to be your traditional parabola. So something like this, and without units, it's hard to say exactly what we're looking at, because parabolas have this interesting property of self-similarity. The other one is a bit more challenging to graph until you factor it into this, x squared minus 6. So one of my roots is going to be x equals 0. My other two roots are going to be x squared minus 6 equals 0, x squared is equal to 6. So x is equal to plus or minus the root of 6, which is somewhere between 2 and 3. Because 2 squared is 4, 3 squared is 9, and 6 is between those. So from the calculator, it gave me around 2.4 or 5 or something. It's actually not going to be very necessary to know what that is at the moment. So all that to say that my roots are these and then these over here. So one of my roots is here, one of my roots is, let's say, negative 2.45, and symmetrically over here as well. So the cubic function has this sort of behavior. There, and there we go. So we're looking for the region that's bounded by those curves. So we're looking for this space here and this space here. Well, you'll notice that the boundaries of those two spaces are defined by these curves, but in different ways. For example, in this first smaller region, the cubic function forms the upper boundary, and the parabola forms the lower boundary. And in this larger region, the parabola forms the upper boundary, and the cubic function forms the lower boundary. Where those boundaries actually begin and end is an important proposition. So we have this x equals 0 apparently, and that's pretty good. But we don't know what these values are. Notice that the negative 2.45 were the roots, but not necessarily where the intersections of the curves occur. So how do you find intersections? All you got to do is you got to set the functions equal to each other to figure out what they have in common. So when is this function, the cubic, the same as or equal to the parabola? Or that's where this is a true statement. So I'm going to move this over to that side, and I get x cubed minus 6x minus x squared. I should have put that in descending order, but oh well. I'm going to factor an x out of this, and now I'll put it in descending order. X squared minus x minus 6 is equal to 0. I'm going to factor this furthermore by using my patented butt cheek method. Coming to a store near you. So x and x, factors of 6 are 3 and 2. Those would be good, because I can get negative 1, negative 3, and positive 2. So this produces a root of x equals 0, crossing of x equals 0. This produces an intersection of x equals 3, and this produces an intersection of x equals negative 2. So now I know that this intersection point is negative 2. As suspected, this is 0, and this intersection point over here is at 3. Well, that's going to be very important in order for me to set up my two integrals based on these intervals. So my first space over here, the smaller space, is going to be the definite integral, the area under the curve, or the sum of infinite rectangles, taken from negative 2 all the way up to 0. So all of these little slices, and these slices have a length defined by upper function minus lower function, or top minus bottom, which in this case is the cubic minus the parabola. So the top function in this region minus the bottom function in that region. This cannot be simplified, so we can just take the antiderivative. So that's 1/4 x to the 4th minus 3x squared minus 1/3 x cubed. Just double check that real quick. Yep, from negative 2 to 0. So my work here is not very organized. I apologize for that. So this was finding the intersection points. This was finding how to graph my function. Here I'm actually finding the area. Okay, and it's very the gory detail here because it's a little monotonous, frankly, but the fundamental theorem of calculus says you know f of 0, or this function, if you call this f minus f of negative 2, which you get, there's my calculator out here, 9, negative 2, 0. I'm plugging in the original function because this is kind of cheating, but It'll just make for a shorter, less boring video, hopefully. 5 1/3 or 16 thirds. So all this stuff would simplify, and you can kind of see where the thirds have come from. 16 thirds. So that's the number of blocks that live in that region. Well, I still have this other region to deal with in my poorly budgeted space. I'll try to fit it in over here. Sure, why not? The integral from, well, let's see, the handoff here is from 0 all the way up to 3. Those are my intersection points. Well, this time my upper function is my parabola. So I'm going to be very careful with my negatives here. X squared is my first function, the upper function, because I'm adding together infinite slices that are dx wide, and it looks like parabola minus cubic, or top minus bottom in this case, would be x squared minus the cubic function minus all of the cubic functions. So I'm going to put that in parentheses there. Dx. Okay, so 0 to 3, if I distribute, I get x squared minus x cubed plus 6x. And then I can take the antiderivative, 1/3 x cubed minus 1/4 x to the 4th plus 3x squared from 0 to 3. F of 3 minus f of 0, where you consider this to be f, would give you, in a perfect world by hand, but in rushed YouTube economy, x squared minus x cubed plus 6x dx. The area of that region is 63/4. And you can kind of see it's a bigger amount, 15.75, in contrast to the 5 1/3 over there. So finally, adding those two areas together, so this is the amount of area in here, and this is the amount of area in there. The total area would be 16 thirds plus 63/4, and I really don't feel like adding fractions at this time of day. So 16 thirds plus 63/4 is 253/12, or approximately 21.083. Alrighty, hope this helps.